This presentation elaborates on the physics-based ground motion simulation methodology adopted by tomorrow's cities in order to quantify seismic hazard effects in Nepal. This methodology is one of the computational components that will be used in order to establish a virtual city platform in which the effect of natural hazards in terms of engineering and social consequences will be investigated. The seismic hazard analysis process involves identifying the seismic sources where future ruptures could occur. The instrumental catalog of earthquakes in Nepal, shown here in this figure, indicates that small, moderate, and large magnitude ruptures could occur across the country. In terms of ground motion modeling aspects of seismic hazard analysis, we can utilize, broadly speaking, two different categories of ground motion models. The first conventional approach is the empirical ground motion models where we can estimate the distribution of ground motion intensity measures for a given configuration of source, site, and path effects. The second approach is the simulation approach, where we can model the rupture and propagation of the waves and the response of the site, and the end products are ground motion time series that we can use directly in engineering risk assessments. The empirical ground motion models that are conventionally used in research and practice are based on the recorded ground motions from past events and an average model that is fitted through the intensity measures of those ground motions with an uncertainty around the average estimates. For regions such as Nepal with limited instruments and instrumentation and recorded ground motions, usually ground motion models from other locations, seismic locations in the world, are usually used with some minor adjustments to the properties of ground shaking in the location of interest. Looking at the progression of empirical ground motion models in the past few decades, we can see that no significant reduction has been apparent in the estimated uncertainty from these ground motion models. This is despite the fact that the number of recordings in the past decades has increased and the complexity of the ground motion has also increased. But due to the simplified way of representing the source, path, and side effects, and also because of the lack of data in the near source regions from large magnitude ruptures, the reduction in uncertainty estimates from the empirical ground motion models are not significant. Here's an example application of empirical ground motions for Nepal for three hypothetical scenarios of magnitude 8, 8.2, and 8.5, as well as magnitude 7.8 Gorka event. As you can see, the ground motions estimated from using these empirical ground motion models are basically uniformly distributed with almost the same value across the rupture plane, and also they decay as you go far away from the rupture plane. However, we know from the Gorka event and so many other events throughout the seismic locations globally that specific characteristics of the site and also specific characteristics of the rupture propagation in terms of directivity they could, and also hypocentral location and the bilateral and unilateral rupture propagation could significantly affect the observed ground motions. However, these empirical ground motion models, they do not have enough capabilities to account for these specific ground motion properties, giving the specific properties of the site and the source. We can utilize these empirical ground motion models in the context of probabilistic seismic hazard analysis. And here's an example of that for Nepal. As you can see, for example, for 2% in 50 years probability of exceedance, the peak ground acceleration shown here is it's not much changing across the country. And this comes from the limitation of these empirical ground motion models in accounting for the specific characteristics of the source, path, and site effects. An alternative approach for ground motion modeling is to use simulation. Here, the focus is on physics-based ground motion simulation methodology in which the regional and site-specific characteristics of the crustal and basin layers, as well as the earthquake source properties, including hypocentral location, slip distribution, and rupture velocity, and etc., are incorporated in the modeling stage in order to solve the equation of motion and obtain the ground motion time series at the surface of the ground so we can use them in the engineering, damage, and risk assessment. The most important aspect of the most important advantage of the physics-based simulation is the framework is that it provides the framework to scrutinize the uncertainties in the underlying parameters that are used for earthquake source, propagation of the waves, and the site response, which will have implication in terms of the hazard and risk measures. The ingredients for physics-based ground motion simulation can be broken down into three: source modeling, which characterizes the spatial and temporal evolution of the rupture; velocity structure, where the geometry and characteristics of the different layers of the crust, as well as sedimentary layers, are specified; and the site response component, where the response of the near surface soil is considered in the models. Physics-based quantification of seismic hazard is one of the components of the virtual city approach for disaster risk reduction, in which the response of the built environment is also characterized by developing physics-based models for the built environment and assessing the damage due to the earthquake scenarios, and at the end, the impact in terms of economical and social loss. Here's an example of physics-based ground motion simulation for magnitude 6 rupture under the Kathmandu city. These are the characteristics of the kinematic rupture model used for this realization of magnitude 6 scenario. This figure shows the release of energy in terms of seismic moment in different parts of the rupture plane, and the evolution, and this one shows the evolution of the rupture from the hypocenter towards the edges of the rupture plane. And this figure shows the direction of direction of rupture for different parts of the rupture plane. The Kathmandu Basin and its basement topography is incorporated in the simulation model using the JICA report data, And the wave propagation properties of the near surface layers inside the Kathmandu are considered based on the 1D velocity profile estimated for the strong motion stations in the Kathmandu Valley. The Kathmandu City team of the Tomorrow Cities is conducting research to better constrain the Kathmandu basin shape and the properties of the near surface and deep crustal structure. The new information the new data from these efforts will enable us to have a more accurate representation of these properties, and hence it will enable us to have higher accuracy in the conducted simulations. The hexahedral mesh that is utilized for this simulation is shown here. The largest element in this simulation is 1,100 meters with polynomial degrees of 5. This gives us 6 points inside each element. The 1D profile utilized for crustal structure comes from the Mahesh 1D profile that is usually used for the earthquake location in Nepal. As I mentioned, the ongoing efforts in the passive seismology group in the Kathmandu city will enable us to have more accurate representation of the crustal structure in the upcoming versions of these simulations. Here is the result of this simulation. Two different sites are noted here, one of them inside the sedimentary basin layer, and this is the ground motion that is simulated for that site, and another one on the stiff side close to the edge of the basin. What you see here is basically, in terms of colors, is the displacement of the ground in the north-south direction, and you can basically observe the difference between the ground motion in these two different sites. The site located inside the basin shows larger amplitudes of ground shaking and pulse-like motions, as well as the ongoing reverberation at the end of the vibration due to the soft soil response. Obviously, these two different ground motions will have different implications in terms of the induced seismic demand and damage in the system. This example basically illustrates the capability of the physics-based simulation in honoring the site-specific characteristics in between different sites, which will have significant differences and implication in terms of the estimated damage and loss and risk measures. If we apply these two ground motions to archetypical concrete structure, we can see the differences in terms of engineering response. While small amplitude ground motion on a stiff site imposes moderate demand on the structure, which doesn't exceed the assumed collapse limit for this structure. We can see in the second animation here that the ground motion on the sedimentary layer imposes disproportionately large demand on this structure, and this demand basically exceeds the collapse limit of this structure. So as part of our virtual city simulation platform, we will basically progress towards utilizing physics-based modeling also for the built environment in order to investigate the effect of differences in the ground motions that will impose different demands on the structure. Our aim is to basically investigate the effect of earthquake scenarios on a city scale on the built environment. Another effort that has been going on is to validate the physics-based ground motion simulations with respect to the observations that, with respect to the scarce ground motion observation and ground displacement observation in the past events, more specifically Gorka and subsequent events. Here is the inverted rupture for the Gorka event from haze. What you can see is the slip, the amount of a slip on the rupture plane, and by conducting physics-based simulation for that for that inverted kinematic rupture, we have estimated these vertical displacement across the rupture plane and out and away from the rupture plane. If we compare these results that are coming from the physics-based simulation with the results of a model based on INSAR and GPS displacements, which are more obviously they are accurate observation of the displacement due to this event, we can see that the trends of positive above 1 meter vertical displacement in which is observed is also replicated and accurately represented in the physics-based simulation. However, if you can see that there are some discrepancies between the simulation and the observed displacement. The simplified 1D structure, velocity structure that is utilized in this simulation, and also the coarse source model that is used in this simulation are basically can be considered as responsible for the inaccuracy with respect to the observation. However, the general trend of displacement shows that the simulations can have closer estimation of the displacement at the surface. We will continue this validation effort with by gathering more information about the Gorka and also subsequent events in order to establish more rigorous framework for understanding the validity of the simulated ground motion and utilizing them in order to estimate the size scenario hazard for the ground motion hazard for the scenario ruptures. The overarching goal of the project is to establish platforms for city-scale rupture-to-rafter simulation of earthquake scenarios and investigate their implication on future city developments. Also, advancing the multi-hazard risk assessment framework in the context of engineering and social loss assessment, loss and risk assessment, and also developing new partnership for stakeholder partnership for disaster risk reduction. In terms of scientific earthquake hazard developments, we will focus on modeling the effect of uncertainty in kinematic rupture models, and by gathering passive seismology data, we will investigate the deeper structure and near surface sedimentary layers in the Kathmandu area in order to establish high quality tomographic model of the Kathmandu and also hopefully the tomographic model of Nepal. Region and site specific simulation of historic and future earthquake scenarios will be conducted in order to have more accurate and reasonable basis for conducting the site-specific engineering and social risk assessments.